All right, so we want to look at inclined planes again. Or maybe this is the first time we've looked at it. But we're going to look at an inclined plane, and we're going to look at an inclined plane with friction. So what we want to study is we want to look at what's going to happen to our block when we have friction with it. And so we're going to set the angle here. We'll say that this angle is 30 degrees. And we'll say that our block, for convenience, has a mass of 1 kilogram. And we want to understand what's the acceleration going to be, if any, for this block going down the inclined plane. Will this block even move? So, we have, whenever we have an inclined plane, we always rotate our reference frame so that the x-axis is parallel to the plane and the y-axis is perpendicular. We know that we have gravity that pulls the block straight down. We have a normal force that acts perpendicular. It's a little bit shady drawn there. But we have a normal force that acts perpendicular to the surface of the block. Between this contact surface and the block, there's a normal force that acts perpendicular to that surface. And then, of course, we are going to end up having a frictional force that's going to oppose our motion. So the first thing we want to do is we want to break our gravity into its components in our new reference. So we have our right angle here. This is g. That theta here is the same as the theta here. So we end up getting a g sine theta parallel to the plane and a g cosine theta perpendicular to the plane. So when we draw in our thing, we get g sine theta parallel, g cosine theta perpendicular. So you can imagine that we have a g sine theta force from gravity pulling it, and that means if gravity is trying to go that way, the frictional force is wanting to oppose it. So we'll start by summing the forces in the y direction, and when we sum the forces in the y, it's going to be equal to MAY. So the sum of the forces in the y is that we have a normal force working up, and we have this g sine theta, cosine theta, pulling it down. So we have n minus mg cosine theta equals MAY. We'll say that the AY value is 0 because our block is not experiencing accelerations in the y direction. So that means that the normal minus mg cosine theta equals 0. Or in this case, the normal is equal to mg cosine theta. And that means the normal is 1 times 9.8 times the cosine of 30. And cosine of 30 is 0.866. So that tells us that the normal force is roughly like 8.5 newtons. Now, this was important because we're going to need the result from the normal force when we sum the forces in the x. So let's look at the forces in the x. When we sum the forces in the x, we get MAX. But what forces do we have to sum? Well, we have our g sine theta pulling in the positive direction. So we have an mg sine theta pulling in the positive direction minus the force of friction, and that has to equal MAX. And we call g sine theta positive because even though you think of g as being in the negative direction because it's pulling straight down, it's causing an acceleration in the positive x direction, so we count it as a positive value. So let's look to see if we're going to experience an acceleration. So we know that mg sine theta minus, well, before we've always defined the frictional force as mu times n. So in this case, the frictional force is going to be mu, and we never said mu, but let's just say that mu is 0.2. Seems like a reasonable number. 0.2 times the normal force, which we said was 8.5. So our frictional force then is going to be 8.5 times 0.2, which looks like it should be close to 1.7 or so. So let's take a look. 0.2 times 8.5, 1.7. So our frictional force has a value of 1.7 newtons. So we can plug in the frictional force is 1.7, and that's MAX. So let's look. mg sine theta, n is 1, g is 9.8, and sine of theta is the sine of 30. So that's the sine of 30 minus 1.7 equals MAX. So sine of 30 is a half times 9.8. This is 4.9 minus 1.7 equals MAX. So this looks as though MAX is equal to 3.2. Since M is 1, AX is 3.2 meters per second squared. So at 30 degrees, the block will accelerate down the plane, but it won't be at 4.9, it'll be at 3.2 because friction is slowing us down a little. Now, the next part we can think about is if we had no friction, it would have been 4.9. So this friction slows us down a little bit. So the result, when we have friction in our system, we always rotate our coordinate system so that the y is perpendicular, the x is parallel. We look at our gravities always pulling straight down, so we make our gravity components into the components in the new y and the new x frame. We look at the sum of the forces in the y because that gives us our normal force, which we're going to end up needing for the friction. We then sum up the forces in the x, and we had gravity trying to pull it down the plane. The frictional force is opposed. So we then wanted to know, is the block accelerating? And it turns out it was, because mg sine theta had a value of 4.9, which is larger than 1.7. So the block experiences a positive acceleration. And of course, for the friction force, we remember that the friction force is mu n. And so we came up with a value of 0.2 for the friction, the coefficient of friction, times our normal, and then we had 1.7 was that, which we used over here. So at 30 degrees, with this coefficient of friction on this block, the block does accelerate down the plane.